Thank you very much, Andy. Okay. Hi, good morning. I'd like to begin by thanking Admiral Han for this unique opportunity. So it's my delight and honor to be here. And what I'll walk you through is a view on the transformation that's happening at GE right now. And specifically about one aspect of the technology called digital twin. So you'll get a combination of two things. You'll get this notion of what this digital transformation means to a 125-year-old company, and you'll see how we apply it for specific technology that makes a significant difference. So let's start first with the motivation. What would move a company with 125 years in a certain direction? Well, there are two things. One is a stick, and one is a carrot. So let's look at the stick. The stick is on the left side. So if you look at global productivity in the industries that we look at, especially those industries around energy, transportation, and healthcare, it significantly declined in the last 5 years, from 2011 to 2015. Significantly. What does that mean? In an environment in which every customer is asking for a decrease in price, because there's not a situation you go into in which a customer says, please increase the price, I'll pay more for it. This significantly impacts your profits. That's the stick. As your profit gets impacted, so does your stock. What's the carrot? The carrot is this thing called the industrial internet or the Internet of Things. That is growing at a fantastic rate, but it's also projected to grow at an incredible rate. Without spending too much time here, just look at the numbers. And what you need to notice is that everyone begins with a B or a T. So the number of things that will be connected, between 20 to 50 billion things. These are not my numbers. I just have at the bottom of that slide maybe 6 or 7 different sources. It gets in easily into the 20s. That many things connected. If you look at the revenue that's created from selling products to companies, Internet of Things products, industrial internet products, that easily goes into the billions to trillions. If you look at the economic value created once those products are sold, those companies in turn sell to their customers easily in the trillions. Easily in the trillions. So that's the carrot. So the stick and the carrot are the motivations. Now, what does that carrot actually tell us? That carrot tells us that if it's the Internet of Things, there's a digital aspect of this that's predominant. What does the stick tell us? Because we're looking at productivity in an industrial space, the industries we look at are very prominent. It's a combination of this digital and industrial capability that's going to add to this productivity and this growth. So let's talk about how we began to face that. We began to face that by trying to understand this notion of exponential technologies. What does that actually mean? Because that's what you see occurring with the industrial internet or the Internet of Things. So an exponential technology is one in which the performance is growing at a fantastic rate while the cost is coming down. And what characterizes these exponential technologies is that thing called these technology curves. It's not just Moore's law. Moore's law takes you up one curve, but then on top of that curve, we build other things. As the memories begin to build, new technologies show up that allow you to build arrays of memories that make them faster. As the speed of transistors level off, the way they group transistors allow you still to have the performance in different ways. If you go to FPGAs, if you go to GPUs. There's those nested S-curves. There's another thing that's unique about this technology. I spent 2 decades in IBM. I started off with processors. I built a processor, and then I used programs I wrote on that processor to build a faster processor. Then I used programs I built on the faster processor to build a faster processor. The technology was building itself. I wrote in software. I started with assembly language, and I wrote compilers to write the assembly language, interpreters to write the compilers, scripting language to write the interpreters. Now I can speak and generate software. The software is building itself. Then I combine the software and hardware together. The technology seems to be building itself. This is the fear most people have about AI. Which other industry do you see that has that? We're in the aircraft industry. Does the steel build itself? If you're in the design industry, does the concrete build itself? No, but in this industry it does. And while it's doing so, the cost is dropping. So the interesting thing, 128 megabytes of memory in 2008 was $99. 128 gigabytes of memory this year is $99. A 1,000-fold increase with no change in price. A very different capability. So what do? We look at these exponential technologies, and then we try to determine how can they change the business value in our industry, because it will. And there's a mismatch of speeds in the industry, so we have to look at these technologies very differently. So a jet engine lasts 40 years, a steam turbine lasts 30 years, wind turbine lasts 20 years, a locomotive lasts 20 years. In IBM, I was there for 20 years. In that time, we went through the PC revolution. We went through Smarter Planet. We went through analytics. We went through cloud. 4 evolutions in 20 years. Every 4 to 5 years, this changes. How long do you keep a cell phone for? So how do you match these two together? It becomes interesting when you do that. So we decided on 2 approaches. One was the notion of making sure we blended these technologies, but the other one, equally as important, was we looked at the cultural aspect of what it meant. Because without the two, it would never succeed. So with that backdrop, I'm going to take you into one technology we call digital twin. And I'll show you how we use that technology to drive the industrial changes we needed. I'll talk about how we created those systems and how we adapt those systems using AI capabilities, using robotics to drive to some of the outcomes we have. Then I'll end by talking about the lessons we learned around the way. So let's talk about the first thing we did. First thing we did was we learned that you had to have an awareness of what was happening. Convince yourself it was real and it was happening, then find the best practices that you could out in the industries that were successful, then adapt it to what you needed. Evolved it to the manner in which you needed to have it happen. So we started with the transformations that we saw in the consumer internet. We looked carefully at this for a number of years, and we saw there were 3 very interesting players, leadership players, and these 3 leadership players actually use the same digital transformation approach to be successful. Those were Google, Amazon, and Apple. When we say leadership, what do we mean? Well, we are obviously a commercial company, so we look at financials as one clear definition of leadership. Now, you look at the numbers there, you see Apple, $216 billion in 41 years. Amazon, $136 billion in 25 years. Google, $90 billion in 19 years. When you look at that and you think it took GE a little over 100 years to get to $100 billion. I was with IBM before. It took IBM 93 years to get to $100 billion. Look at the rate of growth of these companies. Apple itself was $8 billion in 2004. It jumped over $200 billion. There's something happening here. Now let's talk about the approaches they use. Now what I'll do is I'll use Amazon, then I will apply to Apple and to Google. So what did Amazon do? Amazon first started using data in order to try to understand a consumer, then use analytics to drive a behavior in which a consumer purchased, and then found ways to deploy that in other consumer spaces. Now it started with this data all in a very demographic focus. So I looked at groups of customers. I'm looking at a group of people, and if this group of people likes this book, and if you should be a member of that group, then I would suggest that book to you. Started with demographic data, data on groups. It quickly realized to do this right, I had to move to data on individuals. So it went from demographic data to individual data. It looked at what you bought, when you bought it, what you bought on Mother's Day, Father's Day, who sent you things on those days, what different types of commercials or advertisements you selected, where did you send the things to, what did you buy when you bought certain things, what did you group together. It took all of this data and it got a profile on you as an individual. In fact, it was a psychographic profile, a profile of an individual, how you buy, and in what context you buy. It used that to get a model of one, not a model of a group, a model of one. And it has 268 million consumers. So now this model of one, now you apply analytics to try to drive a behavior. It began with segmentation. If you belong in this segmentation and this segment is buying these books, I'll sell you these books. It moved quickly to things like profiling. If I know by the ads you're looking at that you're about to go on a ski trip, I offer you these skis at a discount. Then if you buy the skis, it moves quickly to prediction. If you bought the skis, I should sell you a ski helmet at a discount as well. Then I look exactly the ads we send to you, and I see which ads you select, which ads you don't. And so I know, don't waste my time sending these ads to you. I only send you the ads I think would be most beneficial to you. By doing that, I get the maximum amount of revenue for you, but I reduce the cost. So I get a P&L, a profit and loss, focused on you. So I have a model of one and a P&L of one. Then to move quicker, I put it in a platform. A platform allows me to deliver something at the lowest possible cost as fast as possible. Then I take that platform and I go from books to retail to movies and video to web services. And that's how I get to $136 billion. Then to get more data upon you, I give it to you on a Kindle. You keep the Kindles personal. And so I get more data, so it becomes better. I do the same thing if you look at the Apple approach. Apple created a model of one by looking at your iTunes list. There are 800 million people that use iTunes. I can quickly offer you new songs on the list and see if you buy these sounds. If you buy these sounds, I begin to offer you more sounds like that. I build a profile of you. That's how I get to a model of one. Then the P&L of one is where I go after iTunes. Then on a platform, I go from iTunes to video, to applications, to home, to health. But then I put it on steroids. I give you iPods, iPads, iPhones, and I collect an enormous amount of information about you. I give you watches. With it on steroids, that's how you grow to $216 billion. Google does the same thing. Google gets a profile from you by what you search for in terms of Google search. But there's also YouTube videos, Google Maps, Gmail, all to build that profile, that model of one. Then they use analytics to apply that so they can deliver the right ads to you. In their AdSense business, that's the P&L of one. They put it in a platform, and they go from ads to applications to home to health. That's the pattern that's been used. And it works. So how about if we apply that in the transformation in the industrial state? So what you see here is a jet engine. We normally collect information about the jet engine, but in terms of the fleet, we collect fleet information. Usually when things break or when we worry about the life or performance of something. Now, instead, we collect individual information about each particular engine or each particular turbine. We collect information when it's manufactured, when it's maintained, when it operates, the environment it operates in. We quickly create a model of one. Then we apply analytics to understand how we could look at the efficiency and performance of these things. Before we had fleet analytics. We did that primarily because we didn't know enough. So we made assumptions. So if you have the life of a part, what do? I don't know the environment that the engine is running in, and I don't know the way it's used, so I'll assume things. I'll say, well, I assume in this average environment, with this average usage, that the part would last 3 years. But now I know exactly the environment it's running in, exactly the usage, because I'm collecting that data, so I could predict precisely this part will last 5 years. So I don't need to bring the asset in 3 years to inspect it to find out there's nothing wrong with the part. Also, when I bring the asset in, I know exactly what I should find in terms of damage, and I know the replacement to have and the right engineer to repair it. So I reduce the cost and the time to do that. How about performance? I made assumptions on performance of my gas turbines because I didn't know the environment they would run in, and I didn't know the way they would run. So I'd look at it and I'd say, well, I assume this should be the maximum performance because I want to limit my risk so I don't have damage that would void my contracts. But now I know the exact environment, the exact usage, so I have the ability now to say you can perform at a little higher level at this point in time. So with the understanding of the life, I change the efficiency of the system or availability of the system. The understanding of performance, I change the performance of the system. When I combine those two together, the economics changes. So now I have a P&L of 1. So I have a model of 1 on the asset and a P&L of 1 on the asset, allowing the customer to have the power of taking a specific action at the right time, being more efficient, much better performance, knowing how they can vary that asset to meet their need. Then I put it all in a platform. I call the platform Predix. I make sure that platform has 2 components, a cloud component and an edge component. Why do I need the edge component? Because some of that information has to be delivered in real time. When I run control systems that affect power stations and locomotives and engines, airplane engines, I have to run it in real time. Also, I may do things that require video capabilities. I don't have the bandwidth. So I need an edge capability and a cloud capability. All this I have on Predix, I put it in a platform, again, focusing on speed and time, and I deliver it to aviation, to power, to transportation, to healthcare. It's the same approach that we've used before, except we've evolved it and innovated it specifically for this environment. Let me give you some examples. Because the other aspect of this, because with GE, it's all about business outcomes. It is not the use of technology for technology's sakes, but it's directed specifically towards an outcome. So the digital twin, which is what I just showed you, has 5 characteristics. It is per asset. It is attacking a specific business problem. It is a continuous stream of data. Again, the timing of it is based upon the problem we're attacking. It's adaptive. When the environment changes, it changes. It's scalable. If I get it for one device, I can quickly scale it to things that look similar to that device. It's focused on 3 things. How do I provide sufficient early warning so I can change an unscheduled maintenance to a scheduled maintenance, giving the customer the maximum availability for their asset? Continuous prediction. How do I predict the remaining useful life so that I know exactly when to move that asset out of service and be prepared when I do move it out of service to have all the things I need to reduce the services time? Or how can I predict performance capabilities so that if I see the benefit of a much higher electricity price, I can increase the performance of this gas turbine to take advantage of that? How do I do dynamic optimization, where I balance the needs operationally and business-wise against each other? So those are 3 examples here. So the first one, sufficient early warning, I'll just touch briefly on that. So the notion here is there's a bearing in the engine, the number 4 bearing. And if you can detect early enough that number 4 bearing giving you problems, you can stop a light from showing up on the dashboard that says, you've got to have this repaired. Now, before, the warning was 4 to 6 hours, which can leave a plane stranded on a terminal, out of service, passengers upset. Now, when we create a digital twin and we combine the physical and digital capabilities, and I'll talk about that in a second, we have the warning capability to go from a few hours to a day to 15 to 30 days. That's advanced warning. When I look at continuous prediction, the challenge here is that we were flying these aircraft in hot and harsh environments. Highly contaminated, very hot, maybe sandy environments, ones you find in the Middle East or certain parts of Asia. And the blades that rotate have a coating on them. And that coating was getting contaminated, being worn away, exposing the blade itself. The heat was causing problems. That again results in a warning light. We began to pull these engines every 200 flights to look at them, to determine buildup on the blades. When you pull an engine, it's away from the customer. What we did is we created a digital twin that began to tell us exactly what the level of damage is, the cumulative damage on the blade, by understanding the physics, but also the environment it was flying in, as well as the way it was being flown. What was the thrust when it took off? How much did it climb? Where did it level off? Which 2 airports it flew between? It's combining, again, the physical and the digital to give us an outcome. In this way, I can actually say, after 200 flights, don't bring this aircraft in. The damage was not sufficient. Or I can say at 160 flights, bring this one in. It's been flying continuously in the wrong environments. Damage has built up too much. Third aspect of this is a dynamic optimization. Whenever you bring in one of these aircrafts, what you'd like to do is quickly replace it with a spare engine and put it back out so that the customer has maximized the availability of the aircraft. How do I know if I've bought enough spare engines? It all depends. If I'm keeping the aircraft out there a lot longer, what tends to happen is when I bring it in, there's a lot more damage. I have many more parts to replace. If there are many more parts to replace, I'm going to have to keep it in the shop longer. If I have to keep it in the shop longer, I'm going to need many more spare engines. How do I balance the time I keep it on wing with the damage it gets done with the turnaround time in the shop in such a way that I have the minimal number of spare engines? Because these engines cost a lot. Or if you have to lease an engine, it costs a lot. So you want the balance between the two. That's a dynamic optimization problem with many factors. The outcomes you see here are all real in terms of the numbers. 90+ million saved in continuous prediction, 30 million saved in dynamic optimization. So I'm sure you're asking, how do we do it? What's this notion of physical and digital? Let me simplify it to some level. So the physical aspect of it is the fact that I have certain sensors. And from those physical sensors, I've created certain models, physical models. Those physical models give me data about the asset I'm thinking about. But what I need is more data about this asset. So I create virtual sensors from the digital data I have. Those virtual sensors combined with the physical sensors give me an enormous amount of data that allows me to use machine learning techniques and other techniques to determine some of these new capabilities I never had access to before. For instance, on a jet engine, there may be only 20 sensors. Why are there 20 sensors? A sensor costs over $20 million to build. It's got to last 40 years on the plane. It's got to fly at 10,000 feet. It's got to go through incredible heat. It's got to land and take that jarring impact. It costs a lot. We may have sensors at these 2 points. What occurs in the middle between those 2 sensors to that piece of metal? What if I see that as a problem? I create a virtual sensor that lies right here that I've created because I have data about where it flew, how it flew. And that virtual sensor gives me additional information that allows me to deliver this value. It's the combination of the math and the science, the physical and the digital, coming together to give us this unique capability. So let me talk about learning systems now. Because I'm doing these digital twins, and these digital twins are adapting to the environment. So I have a living model, because the model, every time the plane lands, I get snapshot data. It's living. How about if I can have it learning? How about if the model itself can learn from the environments it's in? So if I have a living learning model, I have the best of all worlds. So where do we see learning happening? Let me use the Tesla example. Tesla right now has something called enhanced autopilot. So if you look at Tesla cars, this is the ability to do, what we talk about as autonomous driving. Now, at the start, we talk a lot about things like Google. Google has 2 million miles with their cars. Well, Tesla, when you look at the entire fleet, as of last year, October, had over 280 million miles of autonomous driving. But it also captures all the data whenever the car drives. It's like a mini computer on wheels. It has over 1.3 billion miles worth of data it's collected. So what is it doing? So if you get in a Tesla, there's a big panel, and this panel has a button that you can push for $5,000 called Enhanced Autopilot. What does the autopilot do? It does several things, but it does 3 things that I personally like. First thing it does is on freeways, it can keep you at a constant speed, and it can change lanes to keep you at that constant speed. How does it do that? There are 16 sensors below the car, there are 48 cameras on the car, and there's a radar in the front of the car. So the radar actually can go and jump ahead and see cars and understand the movement of cars. And the cameras can look at the white lines on the ground, and so it can move you between lanes to keep you at that constant speed. It can also take you off the freeway and take you on the freeway. So when you get on the freeway, the most boring times, the times in which several dangerous accidents occur, you sit in the seat and you relax because this is driving for you. The other feature I like a lot is when you pull up, you can come out of the car and you can tell it park itself. It goes and it parks itself. When you come back out of the venue, you open your cell phone, you hit a button, and the car comes to you. Great features. How does it do it? Let's talk a little bit about that. So here's the one I like. So I'm going on the freeway, and I'm coming down, and I'm using the white lines, and the car is driving correctly, and then I come off and go on a country road in which there's only one line. There's a line in the middle of the country road. So I'm on this country road, I'm on one line, the car drifts. I'm in the driver's seat, I adjust it back. After a while, the road shifts, car drifts, I adjust it back. What does the car do? At that point in time, it recognizes that the human is teaching it. I have moved the car back, it records the exact GPS coordinates and the actions I do, and it sends it up to the cloud. At that point in time, once it gets to the cloud, every other Tesla vehicle knows how to drive on that road. That's a human teaching it how to drive. So it's learning from humans. Now, when it's on a road and the road begins to waver, the sensors are adjusting. The sensors are adjusting because it doesn't want to damage the undercarriage of the car. It also wants to ensure that the shocks as well as the wheels last as long as possible. So it adjusts itself. So it's using the sensors and calibrating against the road, mapping the road, keeping things right. That's learning from the sensors. But at the same time, it takes that information, sends it up to the cloud. So any other Tesla car that drives on that road knows that information. So it looks like magic when you first show up on that road that you've never been on, because it suddenly balances itself and it knows exactly where to go. So it learned from humans, and it learned right away from the sensors. It's also learning from the fleet. The fleet of Tesla cars, 70 to 80,000 strong now, are driving on roads that none of us have driven on. mapping those roads, mapping those conditions. So when we show up, looks effortless. So it learns from the fleet. Last thing it learns from is simulations. So it collects all this data and it puts it in the cloud. What does it do when it puts it in the cloud? It runs machine learning algorithms. What do they look for? They look for patterns. Which patterns are important? Here are the patterns they found. The first pattern is if a ball goes into a road, a child follows it. So if the camera detects a ball, it slows down and continues to slow down because a child is coming behind it. Second pattern it detects if a dog runs into the road, a human follows it. So if it sees a dog and it can recognize the dog, it slows down and continues slowing down because a human is coming behind it. Third pattern is that they travel in groups. So whenever it sees they, it slows down. It learned in Australia that kangaroos can hop over cars. So the kangaroo can come directly at you and hop over the car. That's an anomaly, but it's a good thing to know. So it's using simulation. It's learning from 4 different methods. It's learning from the sensors, it's learning from the simulations, it's learning from the humans, it's learning from the fleet. If you can learn from 4 different modes, you can learn at a much faster rate than anything else on the planet, including humans. We have applied the same capabilities to jet engines. We have capabilities where we're learning from the sensors themselves and can allow us to tune some of the twins that save us millions of dollars. We have some of the capabilities in which we're learning from the simulation. That one I showed you an optimization of the jet engines. We had to run simulations projecting forward to figure out the patterns and allow us to figure that out. We're learning from the fleet. When some engines are flying in these hot and harsh environments, everyone doesn't need to. I can learn from that example and apply it. Transfer learning is the term we use in machine learning. We're also learning from experts. In the number 4 bearing, how do we do it? We look at a certain profile. We constantly monitor that bearing, and we know what's normal. When we see something abnormal, we look in the old rule databases we have to see if it ever occurs. And if we can't find something that tells us why we have this anomaly, we send it off to a chief scientist. She or he types something in. We capture that in text mining. And so we're learning from the human. With these 4 rates of learning, the environment changes. Imagine a situation you're in which you've got to learn at a fantastic rate. Wouldn't this be useful? Let me give you another aspect of the use of the twin, something we call adaptive defense. So the notion is we use this to create a digital ghost. Now, when we think about cyber, we rely on a lot of IT systems to protect us at the boundary so that someone can't come in and fool the sensors or fool the control system. You can fool the sensors by giving it fake data and thus manipulate the control system to do an action, or you can directly send that signal as a control system signal and have the machine do something. So while we depend upon our IT brothers and sisters to help us with this, we also know we have some insights into the machine itself. We have one thing that's very hard to spoof, which is physics. So what you see here are 17 sensors. We have 17 sensors around this combined cycle gas plant that has a gas turbine and a steam turbine. And the 17 sensors are all related by physics. So if I try to fool one of the sensors, like the fuel flow, and because I have a digital twin, I know the relationship between that one and the other 17. So if that one sensor looks strange, that physics relationship looks quite strange as well. And I can respond to it. If they fool 2 or 3 sensors, I can respond to it. 5 or 6, I can respond to that as well. Because I know the physics relationship. It's the Brayton cycle of heat. It's the way physics works. It's not just looking at what the data flow is, it's understanding the data flow and the physics itself. So when I do detect that 4 or 5 of these sensors don't seem to be right, what do? I use the digital twin and I build virtual sensors of what it should be. And I use those virtual sensors to continue controlling the system. So I can detect a problem because I'm using the anomaly detection techniques of the digital twin. I can realize when it's not right because I'm using the physics that I know should happen, so I can locate which one of these sensors are a problem. Then I can isolate the sensor, and I can create virtual ones. So I continue, maybe in a degraded fashion, but I'm not totally put out of play. Another use of the digital twin in the environment it's in. And if I can adapt and I can learn, I can evolve fast enough to be better suited to handle these environments. Because my learning gives me, again, other capabilities to allow me to adapt faster. So now when I think about that, what do I have? I have an immune system. I have an immune system that's learning about the environment and adapting to the environment in a very, very quick way. Now let me talk a little bit about the data that we have to gather. I've talked at length about the fact that we're using physical and digital and combining these two together. What's another exponential technology that I can use that actually helps me with ensuring that my systems are kept at the highest level, but also give me the data that I need? Robotics. So what we've done in GE is we've spent a significant amount of time understanding how we use these capabilities. So while we love the technology itself and we have a fascination for it, our real focus is how do we apply this technology to deliver value that I can monetize in the right way. Here are 3 examples. We have something called the inspection, maintenance, and repair approach. What we do here is we use these robotics to first do inspection, gather the data. We generally want to do this in dull, dirty, dangerous environments. Then we focus on how do they do simple maintenance actions for us, then how do they do more complex repair actions for us. So you see 3 examples here. The first one revolves around this notion of G internal services. So the notion is you bring the engine in, or you have the engine and you'd like the engine to be inspected. I'm using many aviation examples here, but they apply to power, they apply to locomotives, they apply to wind turbines, they apply to healthcare equipment. What you see below that G internal services is something called a turbine surgeon. It's roughly about 2 inches long. It can go inside a complex turbine, and it has sensors that allow it to take video. And that video is connected to an edge device, and on that edge device we have algorithms that can detect certain things: corrosions, porlation, cracks. And so that assists the human being in getting to places where we can't normally go. It can also give us a speed up of 8x in determining a problem. The middle one you see in manufacturing, what you see below is one of the Baxter robots. This is a robot that's helping. It's a collaborative robot, so you can have it in the open with humans. Doesn't need to be in a cage. And it helps build the heavy parts of a chassis. It loads the heavy pieces in the best positions, and then the human goes in and does the wiring parts. So the human doesn't have to lift the heavy pieces and put them in the right places and then go from a physical skill to much more fine-tuned skill. We figured out that if you do that in the right way, what we've done is we've reduced the number of injuries to humans, as well as allow the human to focus on the thing that's most valuable. Again, reducing the time, increasing productivity significantly. The other one you see is the service solutions. We have many situations in which we're putting people in very dangerous environments. So this is a rig. On the rig, there are flare stacks and the other structures in which you've got to go and inspect. So you inspect it either by taking a helicopter and flying around that rig and trying to get a camera to look at certain places, but even so, you don't get all the places, or you send climbers up. Climbers on ropes in which the wind is blowing at 40, 50 miles an hour. Very dangerous environments. How about if we use robots in these environments? And I'll show you an example of this one in the video I have. So the notion here is, can we use these bots with humans? And we think there are 3 steps. The first one is using a robot as a tool. The second is using a robot as a partner. The third is automating the robot to the point in which the bot can do it themselves. And what's the bot doing? It's learning. I'll show you the examples of the bot learning from a human, learning from simulations, learning from its own sensors. The same learning paradigm we talked about before. How do we use this to drive value? So on the left side, our focus here is on aviation. So what we have is a situation where I have an engine. Normally, if I had to inspect that engine, I would have to use this camera called a borescope. It's a little camera on the edge of a tube, and I have a person that actually tries to snake it in. And so you snake it in, but there are parts you can't see. What this robot does is that we take the robot in, we attach it to a part of the turbine, and then we spin the turbine. So now it gets to see every part, because there were parts that were blocked from the borescope because the turbine was actually in the way. Now, because it's spinning very slowly, you can take a full picture of that environment. So we can do an analysis on wing. We don't have to actually pull that off wing to do it. Do it on wing, do it very quickly. Detect a problem early. Then we can take an action early, maybe do a water wash, rather than wait until damage occurs. That actually reduces the overhaul visits, the number of times we have to take the entire engine in by 20%. Other example is one of a turbine, gas turbine. So what we're doing here is that we can take the top off the gas turbine. What we normally have to do then is pull the entire turbine up so that you could look at the bottom side. Now we take the top off and we send a robot in, and that robot walks through that turbine, charting its own path based upon what we've asked it to collect. It collects that data again using a camera, gives us insights. By using that turbine, because we can use it effectively, it's cut downtime cost. And the downtime cost is how fast it takes to actually do that repair by 40%. We use 3 basic areas when we do this. The first is this notion of perception. What perception is, can I give the robot a view of their real-world environment? Can I teach it what the environment is so that it understands how to access an engine, what are the parts in the engine, how do I traverse that engine, how do I do this automated inspection? Because it may encounter something that's different, a blockage in some way, it's got to be smart enough to move around it. Then reasoning. How do I teach it how to find a crack, how to find a spoliation, how to find corrosion? How do I actually have it give me the right data to feed that digital twin? The third is dexterity. How do I have it position the camera in the right way so I get the right images, zoom in the right way? Or if it comes with a tool, how do I have it use that tool to actually repair a crack? So we tend to focus on these 3 things. Let me run a video here to show you what we tend to do. So this is one in which we're teaching a robot to do an inspection. We first start by planning. We ourselves as the human look through what we're trying. This is a flare stack. So we're trying to understand what's the schedule of normal inspection on the flare stack, what's the risk trade-off. If I don't inspect the flare stack, how much does it cost me? And then based on that, we say, okay, maybe I do want to do this inspection at this time right now. So if I want to do this inspection, let me at least get some historical background. Because if I can understand where I saw cracks before and what occurred before, it can give me insights into how I have the robot do what it needs to do. So I look at prior inspection reports. Then I decide, let me go out and do a site survey because I've got to build the robot's world view. So the robot and a human, they go out and we fly this around the flare stack. That tall object is a flare stack. Because we've got to understand and teach it that this is a flare stack. There are things next to it that are relevant but not exactly flare stacks. And so we fly it around. Then we take that data back And we have a human say, these are the areas you look at. This is the angle, this is the zoom. The size of that blue ball is the zoom angle. And you map that out. Then you give it to a computer who determines the flight path that's the optimal one, and the angles that's the optimal one for the robot to do exactly what it needs to do. Then when the computer does that, we give it back to human, and we trace it out for the human. So this is the human and the computer working together to learn how to do a task for the first time. And the human looks at it and says, okay, that sort of makes sense. We want to make sure it's not next to too many things. Then we have the robot go out autonomously on their own and fly around the stack itself. It's smart enough to know when there are variations. If there's a wind gust, here's how I angle myself so that I still get the right angle, but I complete the job. And as it's flying around, it's looking for cracks. It detects a crack. It records a crack. It continues its journey. Regardless of the heat, it doesn't get bored. It doesn't lose focus. It doesn't worry about the jets game. It continues on the path. It can not only do cracks, it can do other things, like corrosion. It can detect it at an early point so that I don't need to replace many things. It can put on different sensors. It can do thermal imagery. Normally, I would have humans do this every 3 or 4 months. I can have the robot do it every week. So I can detect something when it's small, and so it costs a lot less to fix. So I can adapt in my environment a lot quicker. So when I have all of this information, I put it together in a report that both the robot and the human generates. So part of this is robots being used as a tool, the human helping the robot understand what to do. And then over the course of time, guess what? More robots in the fleet talk to each other and figure out how to use their fleet information so that they become smarter. Again, using this learning paradigm to get it smarter, to get it quicker. So with that, I'm going to end, but before I end, let me tell you a bit about the journey, because I think you've seen parts of it here. There are 5 things that we learned along this journey. First aspect of it is that to do this right, you have got to have a new strategic awareness about what's happening around you. When you look at the time frames of 20, 30, 40 years in GE compared to the time frames of the technology, 3, 4, 5 years, something is vastly different there. You've got to blend those together. What do? You have to deliver new ideas about how you do things a lot faster. So the first notion was, okay, let's just do it faster. Maybe I can have people work more hours. People work more days. Doesn't work. First notion is this thing known as a string of pearls. How about rather than people work faster, what about if everyone works on a platform and builds modules as they do work? And if I have a lot of these little modules collected on the platform, when I want a new feature, how about if I just string these modules together, 4 or 5 of them to create a new feature? That's a string of pearls. What if I needed something new? Can I string these 4 together? A new capability. Can I string these 5? A new capability. So we have a way of a distributed community all working on the same platform, putting together and adapting as fast as possible to a situation. Not 4 groups running like hell all in one direction or in 2 directions and trying to respond. The string of pearls idea. The vision aspect is make it believable to me. That's why we use consumer examples. Because when the GE engineers, brilliant aeromechanical engineers, have seen we've done it on the consumer side, could you not apply it here? They agreed. Then they said, no, it's different. It's different. We do things in which people's lives are at stake. Okay, well, Tesla's doing that. People's lives are at stake in a car. Once it becomes believable and you challenge them, then they say, okay, you know what, maybe we need to look at this in a different way. Isn't Tesla building rockets? I mean, isn't that hard to do as well? Maybe we should look at this as well. Then make it repeatable innovation. This notion of projects was predominant in GE. I have 10 projects in my organization, I'm good. Well, what's the outcome? No, no, I have 10 projects. Show me the outcome. Well, here's a chart with 10 projects. That's the outcome. You have to focus on the outcome. So we began in 2014, we did 25,000 twins. 2015, looked at me and said, okay, Colin, how much more can you do? My guys came back and said, okay, we can do 35,000 twins. Whew. He said 250,000. Now what occurs when you have that type of demand, that type of outcome? The projects went away. You couldn't do it using an incremental approach with the projects you had then. So we had to scrap that idea. To get to 250, you have to think differently. None of the projects mattered. Or figure out which few matter and actually deliver what you need to deliver. Be outcome focused. He said it should deliver $100 million worth of value. Everybody stopped. In the end, at 2016, when we actually finished, we had 600,000 plus twins, over $300 million in value. Because once you get the mind shift to an outcome, everything changes. This whole notion of human nature. We have cultures. We've built these cultures all these years. You want me to change the culture? No, Colin. I mean, it's our culture. When do people suspend their culture to try new things? In two times. Chaos and opportunity. We have a chaotic situation. Security change, a 9/11. People suspend their culture. They say, okay, let's do something different. You have a massive opportunity. You go to a Silicon Valley company where each person can make $10 million. Wow, we changed our culture. So we began creating these things. The 250,000 twins was a chaos. How much money you could get was an opportunity. They suspended their culture, not asking you to drop your culture. Suspend it and try a couple new things. Once those things worked, they began to incorporate it in their culture. What was different in this one, though, is that there's a winner-take-all mentality. When you ask about Google, Apple, and Amazon in the commerce, in the entertainment space, or in the advertising space, GE normally would ask, who are the top 3 players? If you ask that question there, who are number 2 and 3, the answer is, it doesn't matter. There's a winner-take-all culture in this world right now, and if you don't have that, you've lost. The last one is you have to make visible manifestations of your organizations. GE moved all of their IT into one centralized organization. No longer the 8 silos. Where I sit in the GRC, the Global Research Center, we package all of these small labs and these projects into 2 big areas, one physical, one digital. And then we create breakout projects in which we fuse the 2 together with an outcome. The outcome is in a year, the outcome is in 2 years, the outcome is in a few months. If it can't be done, we fold them back in. Visible changes to the way we invest, visible changes to the way we reward. So I'll stop here, but this has been the journey for us. We are still on this path. It is a journey that's inevitable for everywhere you look in this industry. So it's one you have to embrace. So with that, I will stop. Thank you very much for your time. It's been my pleasure and honor to be here.